the Karoo Desert in South Africa, endless red plains stretching to the horizon, rocky outcrops jutting from the earth like ancient monuments, sparse vegetation clinging to life in the harsh climate. It's beautiful in a desolate way, peaceful, quiet, but yet at one time it was unrecognizable compared to now. 252 million years ago, this place wasn't a desert. It was a wasteland, a scorched hellscape where temperatures regularly hit 130 degrees Fahrenheit, where acid rain burned through flesh, where the oceans turned toxic and purple, and where 96% of all species on Earth died screaming. Welcome to the early Triassic, the aftermath of the Permian-Triassic extinction event, the worst mass extinction in Earth's history, the moment life nearly ended. And if you think the extinction itself was bad, boy oh boy do I have news for you. Because what came after, what the survivors had to endure for the next 5 million years, that was arguably worse. This is the story of Earth's darkest hour, when the planet became a nightmare, and when the few remaining creatures had to rebuild life from scratch in conditions that would make hell look comfortable. Let's dive in. First, let's set the stage. Because to understand how bad the aftermath was, you need to understand just how catastrophic the extinction itself was. 252 million years ago, the late Permian period, Earth was actually doing pretty well. The supercontinent Pangaea dominated the globe, one massive landmass surrounded by one massive ocean called Panthalassa. And life? Life was thriving. The oceans teemed with trilobites, brachiopods, and early ammonites. The land had massive reptile-like creatures called therapsids, some as big as hippos, and the forests were lush with primitive conifers and ferns. Everything seemed stable, successful. Evolution was humming along nicely. And then the Siberian traps erupted. Now, when I say erupted, I don't mean a volcano. I mean a volcanic event so massive, so prolonged that it makes Krakatoa look like a firecracker. The Siberian traps weren't a single mountain. They were a volcanic province the size of Europe, and they erupted continuously for hundreds of thousands of years. Imagine Europe, the entire thing. Now imagine it covered in lava flows, magma pouring out of countless fissures, releasing gigatons of carbon dioxide, sulfur dioxide, and methane into the atmosphere. For centuries, the immediate effects were catastrophic. Global temperatures spiked by 10 to 15 degrees Celsius. That's 18 to 27 degrees Fahrenheit, which sounds manageable until you realize we're talking about global averages. Equatorial regions? Easily hitting 130 degrees or higher. But the heat was just the beginning. The sulfur dioxide mixed with water vapor in the atmosphere created sulfuric acid, which fell as acid rain, literally burning through vegetation and flesh. The carbon dioxide levels skyrocketed. Ocean chemistry went haywire. The seas became acidic. Corals dissolved. Shellfish couldn't form shells anymore. And then the worst part kicked in. Ocean anoxia. The oceans lost their oxygen. Deep ocean currents that normally circulate oxygen-rich water shut down. Stagnant zones spread, and in those stagnant zones, something horrifying happened. Bacteria that produce hydrogen sulfide took over, the same gas that smells like rotten eggs, except in concentrations high enough to be toxic. The oceans turned purple, yes, purple, from massive blooms of purple sulfur bacteria, and the hydrogen sulfide didn't stay in the water. It bubbled up into the atmosphere, poisoning the air itself. So, let me recap. The planet was cooking. Acid rain was falling. The oceans were toxic and oxygen depleted. And poisonous gas was rising from the seas. 96% of marine species went extinct. 70% of terrestrial vertebrate species died. Insects, which are notoriously hard to kill, lost 70% of their species. It was the closest life on Earth has ever come to total annihilation. And then, somehow, it got worse. Because the extinction event itself lasted maybe 1 to 2 million years, which is quick in geological terms. But the aftermath, the recovery period, that lasted 5 million years. 5 million years of hell on Earth. Let me paint you a picture of what the early Triassic looked like. Starting with the oceans, the marine ecosystems were obliterated. Coral reefs, gone. Wouldn't return for millions of years. Trilobites, which had survived every previous extinction event for 300 million years. Extinct, never coming back. The ocean food chains collapsed. Top predators died. Mid-level predators died. Even the bottom feeders struggled. And what survived? Mostly simple organisms. Limpets, some bivalves, a few species of fish, that's it. And the ocean stayed this way for millions of years. Scientists call it the reef gap, a period where complex marine ecosystems simply didn't exist. The oceans were essentially biological deserts. But the land was even worse. Early Triassic terrestrial ecosystems were absolutely desolate. Most plant life died during the extinction. Forests collapsed, and what grew back? Mostly disaster taxa, that's the actual scientific term. Plants and fungi that thrive in disturbed environments. Massive fungal blooms spread across the dead forests, feeding on the rotting wood, creating landscapes that looked more like alien planets than Earth. And the surviving animals? They had it rough. The dominant land vertebrates before the extinction were therapsids, mammal-like reptiles. Some were carnivores, some were herbivores. And they were diverse, successful. But the extinction called them hard. Only a handful of genera survived. And in the aftermath, one genus dominated like nothing before or since. Lystrosaurus. You've probably never heard of Lystrosaurus. But for a few million years after the extinction, it was the most successful vertebrate on Earth. And by successful, I mean it accounted for 95% of all land vertebrates in some regions. 95%. Imagine a world where one species makes up 19 out of every 20 animals you see. That's not an ecosystem, that's a monoculture. And it's deeply weird. Lystrosaurus was about the size of a pig, had a beak, probably ate roots and tough vegetation, and it survived because it was a generalist, could eat almost anything, could burrow to escape heat, could handle the awful conditions. But even Lystrosaurus struggled. Fossil evidence shows they suffered from disease, malnutrition, and high infant mortality. The world was so harsh that even the most successful animal barely scraped by. And the predators? Even worse off. The main predator of the early Triassic was a group called the archosaurs, early relatives of dinosaurs and crocodiles, but they were small. Scrappy, nowhere near as impressive as what came before or after. The food chains were broken. Simplified, you had Lystrosaurus eating plants, small archosaurs eating Lystrosaurus, that's it. No complexity, no diversity, the entire planet was in survival mode. Now let's talk about why recovery took so long. Because 5 million years is a genuinely long time, even in geological terms. So what kept Earth in this nightmare state? 3 main factors: heat, oxygen, and continued volcanic activity. First, the heat. Global temperatures stayed elevated for millions of years. The carbon dioxide released by the Siberian traps didn't just disappear. It lingered in the atmosphere, creating a sustained greenhouse effect. Equatorial regions remained uninhabitable, too hot for most complex life. The only livable zones were in the mid to high latitudes, which severely limited where life could exist. And this created a brutal feedback loop. Less vegetation meant less carbon dioxide absorption, which meant temperatures stayed high, which meant vegetation struggled to recover, round and round. Second, oxygen levels. Atmospheric oxygen plummeted during the extinction, from about 30% in the Permian to as low as 15% in the early Triassic. For comparison, modern atmospheric oxygen is 21%, and we consider 16% to be the minimum for humans to function. At 15%, you're gasping, struggling, can't exert yourself. Now, imagine being a large reptile trying to hunt in 15% oxygen and 130-degree heat. It's nearly impossible, which is why early Triassic animals were generally small. Limited body size, limited energy expenditure. The oceans had it even worse. Marine oxygen levels stayed low for millions of years. Dead zones persisted, and without oxygen, complex marine ecosystems couldn't rebuild. Third, volcanic activity didn't stop. The Siberian traps kept rumbling, not at extinction level intensity, but enough to keep pumping out carbon dioxide and sulfur dioxide, enough to prevent a real recovery. Some researchers even suggest there were additional, smaller volcanic events during the early Triassic, adding insult to injury. So, Earth was trapped, too hot to recover quickly, not enough oxygen to support large, diverse ecosystems, and continued volcanic disruptions preventing stabilization. It was a planetary-scale disaster that just kept going. But life, as Jeff Goldblum so perfectly put it, finds a way. And slowly, painfully, over those 5 million years, life started to rebuild. The first signs of recovery came in the oceans. Around 2 to 3 million years after the extinction, we start seeing more diverse marine fossils, small fish species diversifying, ammonites making a comeback, bivalves spreading. The reef gap started to close, not with corals yet, but with simple reef-building organisms, sponges, algae, creating structures that other creatures could inhabit. And as marine ecosystems recovered, oxygen levels in the oceans improved, which allowed for larger, more active marine predators. Early ichthyosaurs appeared, fish-shaped reptiles that would dominate Mesozoic oceans. On land, things took longer. Lystrosaurus continued to dominate well into the Middle Triassic, but slowly other herbivores appeared. Rhynchosaurs, early dinosaur relatives called dinosauromorphs, and the predators, they got bigger, more diverse. The archosaurs split into 2 major lineages. One line led to crocodilians, the other led to dinosaurs and eventually birds. Niche partitioning started to return. Different species specializing in different prey sizes, different habitats. The simplified food chains became complex again. Plant life recovered too. Forests regrew, conifers spread, ferns carpeted the ground, and with vegetation came more oxygen production, which created a positive feedback loop. More plants meant more oxygen meant larger animals. Larger animals meant more diverse ecosystems. By the Middle Triassic, around 10 million years after the extinction, Earth was starting to look normal again. Still hot compared to today, still recovering, but functional. Ecosystems were operating. Life was diversifying. And then, the late Triassic rolled around, and the archosaurs split. One group became the crocodile line, massive, armored predators like phytosaurs and rauisuchians. The other group, small, bipedal, mostly unremarkable, the earliest true dinosaurs. Nobody at the time would have guessed those little dinosaurs would inherit the Earth. But another extinction event at the end of the Triassic wiped out the large archosaurs. And the dinosaurs? They survived. And they went on to dominate for the next 160 million years. But that's a story for another time. So, let's step back and look at the big picture. Because the Permian-Triassic extinction and its aftermath teach us something important. Mass extinctions aren't just about what dies, they're about what comes after. The recovery period, the rebuilding, The Permian extinction killed 96% of species. But the 5 million years of hellish conditions that followed? That's what really shaped life's trajectory. Lystrosaurus dominated because it could survive when almost nothing else could. The archosaurs rose because they adapted to low oxygen and high heat. Dinosaurs eventually succeeded because they survived when larger competitors didn't. Extinctions are filters. They don't just kill, they select. And what survives isn't always the biggest or strongest. It's the most adaptable, the most resilient. The early Triassic world was a nightmare: scorching heat, toxic oceans, acid rain, minimal oxygen, simplified ecosystems dominated by a single pig-sized reptile. But from that nightmare, the Mesozoic era was born, the age of dinosaurs, the age of massive marine reptiles and flying pterosaurs. An era that would produce some of the most iconic creatures in Earth's history. All because a handful of species refused to give up, kept surviving, kept adapting, kept pushing forward through conditions that should have killed everything. And that's what makes the early Triassic so fascinating. It's not just a story of death. It's a story of resilience, of life clinging to existence by its fingernails, and eventually, against all odds, thriving again. The worst extinction in history didn't end life. It just hit the reset button. And from that reset came something incredible. So the next time you look at a desert landscape like the Karoo, remember what it once was: a scorched wasteland where temperatures could cook you alive, where the air was toxic and the oceans were dead. And remember what came after: 5 million years of struggle, of survival, of slow, painful recovery. Because Earth has been through worse than anything humans have seen, and it's recovered. Life always finds a way. Though, let me be clear, recovery takes millions of years, not decades, not centuries, millions of years. So maybe let's not test that again, yeah? Thanks for watching. If you enjoyed this deep dive into Earth's darkest period, make sure to subscribe to the channel. We've got tons more extinction events and prehistoric nightmares coming. Hit that notification bell so you never miss when we uncover the next chapter of Earth's brutal history. And drop a comment telling me which extinction event you want covered next. Personally, I'm voting for the late Devonian, because when 75% of species die and we're still not entirely sure why, that's a mystery worth solving. Until next time, keep exploring the deep history of our bizarre, resilient planet. And maybe appreciate that we're not living in the early Triassic. Because trust me, you don't want to live in the early Triassic.